Good evening. Let's read some more before I'm getting too tired. It's 6 p.m. I like to cook hot foods later. I had two old cheap sausages from my deep freeze. I will do later. Something on the floor, piece of plastic. So I start to get tired. So we have to continue tomorrow. So I was to the laundry. And shopping 2 times cola. And actually I need something to drink. So when I'm reading on Wikipedia, I find all kind of random stuff I would like to read. Yes, I was not ready. So this video is mostly just reading. This video is not the English vlog video, but we can do that. I have to change thumbnail. I'm not showing other players. Been very hot. It's still very hot in my apartment. Still 26. That's hot in my world. Because it's not a dry heating, it's a wet heating like a greenhouse. It's like in a jungle. It's a wet hot. That's my airline sim game. I'm going to go broke soon. Let's read this. I need half a minute to get to my bed.
History of mathematics. The history of mathematics deals with the origin of discoveries in mathematics and the mathematical methods and notation of the past. Before the modern age and the worldwide spread of knowledge, written examples of new mathematical developments have come to light only in a few locales. From 3000 BC, the Mesopotamian states of Sumer, Akkad and Assyria, followed closely by ancient Egypt and the Levantine state of Ibla, began using arithmetic, algebra and geometry for purposes of taxation, commerce, trade and also in the field of astronomy to record time and formulate calendars. The earliest mathematical texts available are from Mesopotamia and Egypt, Plinton 322, Babylonian c. 2000 1900 BC. The Rind Mathematical Papyrus, Egyptian c. 1800 BC, and the Moscow Mathematical Papyrus, Egyptian c. 1890 BC. All of these texts mention the so-called Pythagorean triples, so, by inference, the Pythagorean theorem seems to be the most ancient and widespread mathematical development after basic arithmetic and geometry. The study of mathematics as a demonstrative discipline began in the 6th century BC with the Pythagoreans, who coined the term mathematics from the ancient Greek, mathema, meaning subject of instruction. Greek mathematics greatly refined the methods, especially through the introduction of deductive reasoning and mathematical rigor in proofs, and expanded the subject matter of mathematics. Although they made virtually no contributions to theoretical mathematics, the ancient Romans used applied mathematics in surveying, structural engineering, mechanical engineering, bookkeeping, creation of lunar and solar calendars, and even arts and crafts. Chinese mathematics made early contributions, including a place value system and the first use of negative numbers. The Hindu-Arabic numeral system and the rules for the use of its operations, in use throughout the world today, evolved over the course of the first millennium AD in India and were transmitted to the Western world via Islamic mathematics through the work of Muhammad ibn Msa with Makron al-Khwarizm. Islamic mathematics, in turn, developed and expanded the mathematics known to these civilizations. Contemporaneous with but independent of these traditions were the mathematics developed by the Maya civilization of Mexico and Central America, where the concept of zero was given a standard symbol in Maya numerals. Many Greek and Arabic texts on mathematics were translated into Latin from the 12th century onward, leading to further development of mathematics in medieval Europe. From ancient times through the Middle Ages, periods of mathematical discovery were often followed by centuries of stagnation. Beginning in Renaissance Italy in the 15th century, new mathematical developments, interacting with new scientific discoveries, were made at an increasing pace that continues through the present day. This includes the groundbreaking work of both Isaac Newton and Gottfried Wilhelm Leibniz in the development of infinitesimal calculus during the course of the 17th century. Table of numerals. European, descended from the West Arabic, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Arabic Indic. Eastern Arabic Indic, Persian and Urdu. Devanagari, Hindi. Bengali. Chinese Japanese. Tamil. Prehistoric, edit. The origins of mathematical thought lie in the concepts of number, patterns in nature, magnitude, and form. Modern studies of animal cognition have shown that these concepts are not unique to humans. Such concepts would have been part of everyday life in hunter-gatherer societies. The idea of the number concept evolving gradually over time is supported by the existence of languages which preserve the distinction between 1, 2, and many, but not of numbers larger than 2. The Ishango bone, found near the headwaters of the Nile River, northeastern Congo, may be more than 20,000 years old and consists of a series of marks carved in 3 columns running the length of the bone. Common interpretations are that the Ishango bone shows either a tally of the earliest known demonstration of sequences of prime numbers or a 6-month lunar calendar. Peter Rudman argues that the development of the concept of prime numbers could only have come about after the concept of division, which he dates to after 10,000 BC, with prime numbers probably not being understood until about 500 BC. He also writes that no attempt has been made to explain why a tally of something should exhibit multiples of 2. Prime numbers between 10 and 20, and some numbers that are almost multiples of 10. The Ishango bone, according to scholar Alexander Marshak, may have influenced the later development of mathematics in Egypt as, like some entries on the Ishango bone, Egyptian arithmetic also made use of multiplication by 2. This, however, is disputed. Predynastic Egyptians of the 5th millennium BC pictorially represented geometric designs. It has been claimed that megalithic monuments in England and Scotland, dating from the 3rd millennium BC, incorporate geometric ideas such as circles, ellipses, and Pythagorean triples in their design. All of the above are disputed, however, and the currently oldest undisputed mathematical documents are from Babylonian and dynastic Egyptian sources. Babylonian, edit. Main article, Babylonian Mathematics. See also, Plimpton 322. Babylonian mathematics refers to any mathematics of the peoples of Mesopotamia, modern Iraq, from the days of the early Sumerians through the Hellenistic period almost to the dawn of Christianity. The majority of Babylonian mathematical work comes from two widely separated periods. The first few hundred years of the 2nd millennium BC, Old Babylonian period, and the last few centuries of the 1st millennium BC, Seleucid period. It is named Babylonian mathematics due to the central role of Babylon as a place of study. Later under the Arab Empire, Mesopotamia, especially Baghdad, once again became an important center of study for Islamic mathematics. In contrast to the sparsity of sources in Egyptian mathematics, knowledge of Babylonian mathematics is derived from more than 400 clay tablets unearthed since the 1850s. Written in cuneiform script, tablets were inscribed whilst the clay was moist, and baked hard in an oven or by the heat of the sun. Some of these appear to be graded homework. The earliest evidence of written mathematics dates back to the ancient Sumerians, who built the earliest civilization in Mesopotamia. They developed a complex system of metrology from 3000 BC that was chiefly concerned with administrative /financial counting, such as grain allotments, workers, weights of silver, or even liquids, among other things. From around 2500 BC onward, the Sumerians wrote multiplication tables on clay tablets and dealt with geometrical exercises and division problems. The earliest traces of the Babylonian numerals also date back to this period. The Babylonian mathematical tablet Plimpton 322, dated to 1800 BC. Babylonian mathematics were written using a sexagesimal, base 60, numeral system. From this derives the modern-day usage of 60 seconds in a minute, 60 minutes in an hour, and 366 degrees in a circle, as well as the use of seconds and minutes of arc to denote fractions of a degree. It is thought the sexagesimal system was initially used by Sumerian scribes because 60 can be evenly divided by 2, 3, 4, 5, 6, 10, 12, 15, 20 and 30, and for scribes, doling out the aforementioned grain allotments, recording weights of silver, etc., being able to easily calculate by hand was essential, and so a sexagesimal system is pragmatically easier to calculate by hand with. However, there is the possibility that using a sexagesimal system was an ethno-linguistic phenomenon that might not ever be known, and not a mathematical /practical decision. Also, unlike the Egyptians, Greeks, and Romans, the Babylonians had a place value system, where digits written in the left column represented larger values, much as in the decimal system. The power of the Babylonian notational system lay in that it could be used to represent fractions as easily as whole numbers. Thus multiplying two numbers that contained fractions was no different from multiplying integers, similar to modern notation. The notational system of the Babylonians was the best of any civilization until the Renaissance, and its power allowed it to achieve remarkable computational accuracy. For example, The Babylonian tablet YBC 7289 gives an approximation of square root 2 accurate to 5 decimal places. The Babylonians lacked, however, an equivalent of the decimal point, and so the place value of a symbol often had to be inferred from the context. By the Seleucid period, the Babylonians had developed a zero symbol as a placeholder for empty positions, however it was only used for intermediate positions. This zero sign does not appear in terminal positions, thus the Babylonians came close but did not develop a true place value system. Other topics covered by Babylonian mathematics include fractions, algebra, quadratic and cubic equations, and the calculation of regular numbers, and their reciprocal pairs. The tablets also include multiplication tables and methods for solving linear, quadratic equations and cubic equations, a remarkable achievement for the time. Tablets from the Old Babylonian period also contain the earliest known statement of the Pythagorean theorem. However, as with Egyptian mathematics, Babylonian mathematics shows no awareness of the difference between exact and approximate solutions, or the solvability of a problem, and most importantly, no explicit statement of the need for proofs or logical principles. Egyptian, edit. Main article, Egyptian mathematics. Egyptian mathematics refers to mathematics written in the Egyptian language. From the Hellenistic period, Greek replaced Egyptian as the written language of Egyptian scholars. Mathematical study in Egypt later continued under the Arab Empire as part of Islamic mathematics, when Arabic became the written language of Egyptian scholars. Archaeological evidence has suggested that the ancient Egyptian counting system had origins in sub-Saharan Africa. Also, fractal geometry designs which are widespread among sub-Saharan African cultures are also found in Egyptian architecture and cosmological signs. The most extensive Egyptian mathematical text is the Rhind Papyrus, sometimes also called the Alms Papyrus after its author, dated to c. 1650 BC but likely a copy of an older document from the Middle Kingdom of about 1800 BC. It is an instruction manual for students in arithmetic and geometry. In addition to giving area formulas and methods for multiplication, division and working with unit fractions, it also contains evidence of other mathematical knowledge, including composite and prime numbers, arithmetic, geometric and harmonic means, and simplistic understandings of both the sieve of Eratosthenes and perfect number theory, namely, that of the number 6. It also shows how to solve first-order linear equations as well as arithmetic and geometric series. Another significant Egyptian mathematical text is the Moscow Papyrus, also from the Middle Kingdom period, dated to c. 1890 BC. It consists of what are today called word problems or story problems, which were apparently intended as entertainment. One problem is considered to be of particular importance because it gives a method for finding the volume of a frustum, truncated pyramid. Finally, the Berlin Papyrus 6619, c. 1800 BC, shows that ancient Egyptians could solve a second-order algebraic equation. Greek, edit. Main article, Greek mathematics. The Pythagorean theorem. The Pythagoreans are generally credited with the first proof of the theorem. Greek mathematics refers to the mathematics written in the Greek language from the time of Thales of Miletus, 600 BC, to the closure of the Academy of Athens in 529 AD. Greek mathematicians lived in cities spread over the entire eastern Mediterranean, from Italy to North Africa, but were united by culture and language. Greek mathematics of the period following Alexander the Great is sometimes called Hellenistic mathematics. Greek mathematics was much more sophisticated than the mathematics that had been developed by earlier cultures. All surviving records of pre-Greek mathematics show the use of inductive reasoning, that is, repeated observations used to establish rules of thumb. Greek mathematicians, by contrast, used deductive reasoning. The Greeks used logic to derive conclusions from definitions and axioms, and used mathematical rigor to prove them. Greek mathematics is thought to have begun with Thales of Miletus, c. 624 c.546 BC, and Pythagoras of Samos, c. 582 c. 507 BC. Although the extent of the influence is disputed, they were probably inspired by Egyptian and Babylonian mathematics. According to legend, Pythagoras traveled to Egypt to learn mathematics, geometry, and astronomy from Egyptian priests. Thales used geometry to solve problems such as calculating the height of pyramids and the distance of ships from the shore. He is credited with the first use of deductive reasoning applied to geometry, by deriving 4 corollaries to Thales' theorem. As a result, he has been hailed as the first true mathematician and the first known individual to whom a mathematical discovery has been attributed. Pythagoras established the Pythagorean school, whose doctrine it was that mathematics ruled the universe and whose motto was all is number. It was the Pythagoreans who coined the term mathematics, and with whom the study of mathematics for its own sake begins. The Pythagoreans are credited with the first proof of the Pythagorean theorem, though the statement of the theorem has a long history, and with the proof of the existence of irrational numbers. Although he was preceded by the Babylonians, Indians and the Chinese, the Neo-Pythagorean mathematician Nicomacheus, 6120 AD, provided one of the earliest Greco-Roman multiplication tables, whereas the oldest extant Greek multiplication table is found on a wax tablet dated to the 1st century AD, now found in the British Museum. The association of the Neo-Pythagoreans with the Western invention of the multiplication table is evident in its later medieval name, the Mensa Pythagorica. Plato, 428/427 BC 348/347 BC, is important in the history of mathematics for inspiring and guiding others. His Platonic Academy, in Athens, became the mathematical center of the world in the 4th century BC, and it was from this school that the leading mathematicians of the day, such as Eudoxus of Cnidus, c. 390, c. 340 BC, came. Plato also discussed the foundations of mathematics, clarified some of the definitions, for example that of a line as breadthless length, and reorganized the assumptions. The analytic method is ascribed to Plato, while a formula for obtaining Pythagorean triples bears his name. Eudoxus developed the method of exhaustion, a precursor of modern integration and a theory of ratios that avoided the problem of incommensurable magnitudes. The former allowed the calculations of areas and volumes of curvilinear figures, while the latter enabled subsequent geometers to make significant advances in geometry. Though he made no specific technical mathematical discoveries, Aristotle, 384 c. 322 BC, contributed significantly to the development of mathematics by laying the foundations of logic. In the 3rd century BC, the premier center of mathematical education and research was the Museum of Alexandria. It was there that Euclid, c. 300 BC, taught and wrote the Elements, widely considered the most successful and influential textbook of all time. The Elements introduced mathematical rigor through the axiomatic method and is the earliest example of the format still used in mathematics today, that of definition, axiom, theorem, and proof. Although most of the contents of the Elements were already known, Euclid arranged them into a single, coherent logical framework. The Elements was known to all educated people in the West up through the middle of the 20th century, and its contents are still taught in geometry classes today. In addition to the familiar theorems of Euclidean geometry, The Elements was meant as an introductory textbook to all mathematical subjects of the time, such as number theory, algebra and solid geometry, including proofs that the square root of 2 is irrational and that there are infinitely many prime numbers. Euclid also wrote extensively on other subjects, such as conic sections, optics, spherical geometry, and mechanics, but only half of his writings survive. Archimedes used the method of exhaustion to approximate the value of pi. Archimedes, c. 287-212 BC, of Syracuse, widely considered the greatest mathematician of antiquity, used the method of exhaustion to calculate the area under the arc of a parabola with the summation of an infinite series, in a manner not too dissimilar from modern calculus. He also showed one could use the method of exhaustion to calculate the value of pi with as much precision as desired, and obtained the most accurate value of pi then known, 3 plus 10 / 71. While he is also known for his contributions to physics and several advanced mechanical devices, Archimedes himself placed far greater value on the products of his thought and general mathematical principles. He regarded as his greatest achievement his finding of the surface area and volume of a sphere, which he obtained by proving these are 2/3 the surface area and volume of a cylinder circumscribing the sphere. Apollonius of Perga, c. 262-190 BC, made significant advances to the study of conic sections, showing that one can obtain all 3 varieties of conic section by varying the angle of the plane that cuts a double-lapped cone. He also coined the terminology in use today for conic sections, namely parabola, place beside or comparison, ellipse, deficiency, and hyperbola, a throw beyond. His work Conics is one of the best known and preserved mathematical works from antiquity, and in it he derives many theorems concerning conic sections that would prove invaluable to later mathematicians and astronomers studying planetary motion, such as Isaac Newton. While neither Apollonius nor any other Greek mathematicians made the leap to coordinate geometry, Apollonius' treatment of curves is in some ways similar to the modern treatment, and some of his work seems to anticipate the development of analytical geometry by Descartes some 1800 years later. Around the same time, Eratosthenes of Cyrene, c. 276-194 BC, devised the sieve of Eratosthenes for finding prime numbers. The 3rd century BC is generally regarded as the golden age of Greek mathematics, with advances in pure mathematics henceforth in relative decline. Nevertheless, in the centuries that followed, significant advances were made in applied mathematics, most notably trigonometry, largely to address the needs of astronomers. Hipparchus of Nicaea, c. 190-120 BC, is considered the founder of trigonometry for compiling the first known trigonometric table, and to him is also due the systematic use of the 360-degree circle. Heron of Alexandria, c. 1070 AD, is credited with Heron's formula for finding the area of a scalene triangle and with being the first to recognize the possibility of negative numbers possessing square roots. Menelaus of Alexandria, c. 100 AD, pioneered spherical trigonometry through Menelaus' theorem. The most complete and influential trigonometric work of antiquity is the Almagest of Ptolemy, c. AD 9168, a landmark astronomical treatise whose trigonometric tables would be used by astronomers for the next 1,000 years. Ptolemy is also credited with Ptolemy's theorem for deriving trigonometric quantities, and the most accurate value of pi outside of China until the medieval period, 3.1416. Following a period of stagnation after Ptolemy, The period between 250 and 350 AD is sometimes referred to as the Silver Age of Greek mathematics. During this period, Diophantus made significant advances in algebra, particularly in determinate analysis, which is also known as Diophantine analysis. The study of Diophantine equations and Diophantine approximations is a significant area of research to this day. His main work was the Arithmetica, a collection of 150 algebraic problems dealing with exact solutions to determinate and indeterminate equations.